Here at the Department of Energy's Argonne National Laboratory, we accelerate the science and technology that drives U.S. prosperity and security.
We work in one-of-a-kind, state-of-the-art scientific facilities to better understand our world and help make our lives healthier and safer.
At Argonne, our world-class scientists and engineers are tackling the biggest problems facing us today.
By deciphering microscopic structures inside materials and chemicals, we can greatly improve our quality of life.
We're also enhancing vast transportation networks to connect us more efficiently to jobs, healthcare, education, and leisure.
By looking backwards, we can understand how the origin and evolution of the universe gave us the matter that makes up humanity.
And by looking forward, we can predict extreme weather events to help us adapt our essential energy, water, and telecommunication systems.
We are building disruptive computing technology that delivers unprecedented speed, automation, and connectivity.
And by working in harmony with our government, academic, and industry partners, we can better deploy these innovations.
At Argonne National Laboratory, we work hard to advance science, secure energy, and fuel growth for a better today and tomorrow.
Good evening, everyone. Welcome to Argonne National Laboratory. I'm Robyn Grange, and I'm the Director of the Office of Community Engagement here at Argonne. As you just saw in our opening video, Argonne is at the forefront of scientific discoveries that are positively impacting our society. This evening's program puts a spotlight on the exciting research and discoveries being led by some of our early career scientists. For nearly 80 years, Argonne's talented scientists and engineers have been using cutting-edge technologies, and working together, they are seeking to answer the biggest questions facing humanity, from reducing greenhouse gas emissions, which you'll hear about a little later on this evening, to modernizing the electric grid and unraveling the origins of the universe. Argonne is helping to overcome some of the world's greatest challenges. Argonne's Office of Community Engagement produces the OutLoud public lecture series to share our cutting-edge research and pivotal discoveries with you, our science-curious community. So let's begin with a few housekeeping notes. For our virtual audience, when you joined, your camera and your mic were automatically off. If you experience volume issues, please make sure to unmute your audio and use the volume bar in the Vimeo screen. If you want to use closed captioning, there is a button you can select on the lower right-hand side of your screen. Captioning is not always perfect, especially with some of the scientific terms that are going to be used this evening, so please bear with it. And if you're having any trouble, please send an email to outloud@anl.gov, and we will help you troubleshoot. For our in-person audience, we are recording the event, so by participating, you are consenting to be recorded. And this recording is going to be made available to you on Argonne's YouTube channel within a week. Now, it's important for us to keep in mind safety, so whether you're joining us here in person or at home, take a moment to locate your nearest emergency exits. Lastly, for our in-person and online guests, we operate here at Argonne under a code of conduct. Our code of conduct is really embodied in our core values of impact, safety, integrity, respect, and teamwork. And they define who we are. They guide our decision-making and govern how we act as a community of employees, collaborators, users, students, vendors, and visitors. We are committed to creating and sustaining a welcoming and inclusive environment. It is expected that we treat each other with respect, professionalism, and civility. So thank you so much for participating. So now that we've gotten the housekeeping out of the way, it's my pleasure to introduce Sean Jones, Deputy Laboratory Director for Science and Technology here at Argonne. In this role, he serves as Argonne's Chief Research Officer and its Senior Science Strategist and Advisor. He works with the laboratory leaders to implement a lab-wide science strategy and further develop Argonne's $1.1 billion multidisciplinary science and technology portfolio, which is comprised of 21 research divisions, 6 national scientific user facilities, and over 1,700 research and technical staff. He has more than 30 years of experience in research and development across areas that include academia, industry, and the federal government. We are delighted to have him here tonight to serve as our moderator for the program. And so if you would, please join me in welcoming Sean Jones.
Thank you so much, Robyn. Welcome, everyone, to our Out Loud Public Lecture Series. It's a pleasure to host today's program, both in person and virtually. Our hybrid format allows us to share our cutting-edge research with a wider audience. For those in person, we hope you enjoyed seeing the more than 50 submissions for our Art of Science contest. The collection gives a glimpse into the awe and the wonder that scientists experience when they look into a microscope or when they map out the cosmos. It's an exceptional display of the aesthetics of Argonne science and technology. Now, this past August, we held an annual Postdoc Research Slam, a competition where postdoctoral fellows are challenged to deliver a compelling 3-minute presentation of their research in plain language. I can tell you that's no easy feat. It was a lively event blending poetry slam inspiration with scientific innovation. A diverse panel of Argonne staff and leaders judged the competition, and tonight we'll hear from our third place winners and our first place winner. Shilpika won third place for her presentation on error-proofing supercomputers. And Mokhtar Rashwan also won third place, and he won third place for his talk on capturing carbon dioxide from the Earth's surface. And Bethany Dean-Kersten won first place for her speech on recycling nuclear fuel. Now, before our researchers present on these topics, let me briefly discuss how Argonne is leading in these 3 scientific fields. Since 2006, Argonne Leadership Computing Facility has provided some of the most powerful supercomputers in the world for open scientific research. In fact, we're close to fully installing Aurora, which is currently the fastest supercomputer on the planet. The supercomputers that we house, which in Aurora's case takes up approximately 2 basketball courts and weighs about 600 tons, really speeds up the pace of discovery and innovation in a broad range of disciplines. They are game changers in how we will do science in the future. Yet, like our personal computers, they do malfunction from time to time. Shilpika will actually focus her presentation on how she is using artificial intelligence to ensure reliability, functionality, and efficiency in future machines. Argonne is also leading the effort to help America be more resilient against the effects of climate change. To halt and ultimately reverse the harmful effects of climate change, we are employing new innovations and deploying carbon capture technologies. Mokhtar will talk about the exciting possibilities of carbon capture. He'll review how these technologies will reduce emissions from our atmosphere and enable clean energy future for everyone by deploying and developing new materials for direct air capture of carbon dioxide from the atmosphere. Lastly, Bethany will discuss Argonne's oldest research field and one of its earliest challenges, how to handle used nuclear fuel. She and other researchers are tackling this problem head on. They're developing innovative processes and technologies that recycle used nuclear fuel. This untapped energy source could generate enough clean energy to power tens of millions of homes. Our research is especially important right here locally in Illinois, which is the leading producer of nuclear power in the United States, and about 50% of our electricity actually comes from nuclear power, the power of splitting atoms. Now, we appreciate Shilpika and Mokhtar and Bethany for sharing their research with us tonight. The work of early career researchers, like our tonight's speakers, furthers Argonne's mission of solving global problems through research and development and accelerating the science and technology that drives U.S. prosperity as well as national security. They are at the forefront of tackling pressing global challenges from climate change to energy sustainability, as demonstrated by their pioneering projects. Tonight's lecture will give you a preview of their impactful work. It's an exciting time in these fields, and we're pleased to introduce you to these early career scientists and their impactful research. Whether you're in person or online, please feel free to ask questions during the Q&A period. Your participation is vital to this event's success and to meeting our broader goal of encouraging scientific exploration. Thank you again for being here. Now with that, I'll ask Shilpika to join me on the stage and kick off our evening with the first of 3 presentations. Shilpika, I turn it over to you.
Thank you, Sean, for the introduction. Good evening, everyone. Imagine you're in the middle of a hiking or a camping trip, and your only contact to the outside world is your phone. What would you do if your phone failed? Or perhaps you're working on a deadline on a laptop, and suddenly it freezes, shuts down, and you're unable to turn it on. Days or months worth of effort hidden, or worse, lost in your laptop. These issues are uncommon, but they're not impossible. And they can happen to every kind of technology, even the world's most powerful computers. Now imagine what would happen if a supercomputer failed. You may ask, why is it important for a supercomputer to not fail? Let's take a step back. We can think of Argonne as a digital realm, a large-scale computing facility where countless data transactions, research applications run every second. Argonne's vast infrastructure supports a large research base across backgrounds such as biology, physics, chemistry, cosmology, making it a colossal, intricate, and interconnected labyrinth of servers, databases, network infrastructure, and applications. In other words, supercomputers here at Argonne helps us facilitate high-speed computations of cutting-edge research that helps us keep up with the growing complexity of problems faced at a global scale, such as COVID, climate change, and cancer. Now, whose job is it to look after the supercomputer and ensure smooth operations and minimize failures? It's mainly the operations team. And the operations team here face a relentless challenge of maintaining healthy supercomputers. But despite their best efforts, occasional failures arise, leading to slow operations, unexpected errors, and occasional crashes. My team has been working towards solving this series of failures. We proposed an initiative to dig deep into the labyrinthine log data. We believe that within the terabytes of log data generated daily lay clues needed to diagnose and prevent these issues. Now, log data are monitoring information collected from various sensors within the supercomputer. And also to give you an idea of how big a terabyte is, let's take a standard Word document with 12-point font size and Times New Roman font in your laptop. Now, to fill one page of that Word document, we would require 11,000 bytes of data. A terabyte is 1 trillion bytes. So to fill a terabyte of data in the same Word document, we would require 83 million pages. That is the scale of data we deal with every day, and it keeps growing. The solution we designed, developed, created, and implemented involves intelligent visual analytics tools that's backed up by cutting-edge research, including artificial intelligence, that displays the results of our analysis through intuitive and interactive visualizations. Now, before we go ahead with the cool visualizations, we have the daunting task of processing the raw data collected from hundreds or even thousands of sensors within the supercomputer. The data processing task is not trivial because the type of data that's collected from the sensors and the log data happen to be varied in nature. So one approach is to process these data types separately and to then ensure we combine the results either analytically or visually. We can then look at error counts in the system over time, plotted on a clock face view. Temperature readings plotted on individual components in the supercomputer, and error messages that are filtered and grouped using text-based analysis methods. An amalgamation of these varied visual analytics solutions for varied data types results in an intuitive and interactive solution. Say, for example, there is a spike in the temperature at a particular node in the supercomputer. We can then look at the error distribution over time on the clock face view and the corresponding error messages in the text-based view. We also use advanced analysis techniques and harness the power of artificial intelligence. We do so by aggregating and parsing the data and transforming it into meaningful insight. Now, the operations team don't easily trust the solutions provided by the AI methods, and rightfully so. They want to know why an AI model is telling them that a node is going to fail. So we include human reasoning in our pipeline. What do we mean by human reasoning? Say we have an AI or an artificial intelligence model, and it's given an input and it gives us an output. What happens within the model is usually hidden, a black box. We must first understand the inner mechanisms of the AI model. Second, explain the path from the input to the output in human terms using additional methodologies. Our human reasoning approach would then result in AI models that would explain their own solutions. We also incorporate feedback from the operations experts to refine the solutions that we provide. And the best part is we provide our solutions in real time. All of this results in a holistic pipeline that's seamlessly usable across multiple large-scale computing systems and projects, leading to more efficient systems and reducing energy consumption. We can then do faster, more reliable science, such as weather forecasting, drug discovery, cancer research, material design, and more. Now imagine you're working on your laptop on that deadline, and suddenly an indicator goes, hey, there's a potential problem that's predicted to occur in an hour or a day. You would then make sure that your work is backed up and saved beforehand. Our goal is to ensure that supercomputers are robust to unexpected failures. We do so by looking at the organs of the supercomputer, meaning the nodes and the network connections, and ensure that the data and information flow is correct and reliable. A researcher can now go on a hiking trip while their application is running on an ANL machine and be assured that the supercomputer will do its job and hopefully their phone will do the same. Thank you.
Thank you. Yeah. Thank you so much, Shilpika. We will now transition to Mokhtar Rashwan to give us a presentation entitled Carbon Dioxide Direct Air Capture. Mokhtar, I turn it over to you.
Certified. Thank you, Sean, for the introduction. Good evening, everyone. It's hot today, isn't it? So the big question that we might be asking ourselves is, why is it so hot? Or more specifically, why it has been so hot in the last 1 to 2 decades? Well, the answer lies in our atmosphere. So as you might know, our atmosphere is a mix of a bunch of different gases, and some of these gases absorb the sunlight, and instead of reflecting it back, they trap it, heating up our Earth's surface. Therefore, we call them greenhouse gases. And these are the main cause for the global warming and the drastic climate changes we have been experiencing recently. So the climate changes have become a real fact. And here are some figures or numbers I got from the NASA website. They are like alarming that the climate changes is a serious challenge. So for example, our global temperature increased by about around 1.4 degrees C since the pre-industrial era. And also, the ocean warmed by millions of trillions of joules of heat. So lots of heat is pumped into the ocean. So this heat is equivalent to the total energy from the sun that's like striking our Earth's surface. So this huge amount of heat expands the ocean and seawater, and that's what's causing the sea level to rise. So in the last 3 decades, there were like 4 inches of rise of the sea level. In addition to that, the Arctic Sea ice decline rate is around 12.2% per decade since 1979. So in addition to that, related to the climate change, there have been several recent disasters related to the climate change, from the increased frequency and intensity of the wildfires, tornadoes, and floodings, in addition to the disappearance of some lakes like the Lake Albert in the state of Oregon in 2022. So having these alarming numbers and the disasters I mentioned, so these are like alarming that the climate changes are like very serious, and we have to put more effort to combat it. And as I mentioned, it's all about these greenhouse gases. So among all the greenhouse gases, carbon dioxide has the lion's share as the major contributor to the global warming due to its increased emissions that urged scientists, decision makers, and big energy companies to look for different ways to cut these emissions from the atmosphere. And one promising technology to do so is what we call direct air capture, or abbreviated as DAC, DAC, where certain chemicals or materials can capture or take up carbon dioxide directly from the atmosphere, same way as a piece of charcoal sucks a bad smell from a fridge. So the direct air capture technology has some advantages. For example, it doesn't need a vast land to operate. It can also operate or work at different temperatures, making it suitable for different environments and also for our ambient conditions. And on top of that, the DAC materials, or the direct air capture materials, can be easily fit or incorporated into industrial direct air capture plants. And there are already existing a number of existing plants worldwide for direct air capture, and 2 of them exist here in the United States. And there is an ongoing work for a massive project called DAC-1 here in the United States that's supposed to start by 2025 with an expected capture or capturing capacity of about 1 megaton of carbon dioxide per year. And that's developed by 1.5 company, a big company in the carbon dioxide capture and storage, and invested by the United Airlines. So yeah, how does this process work, the direct air capture of carbon dioxide? So simply, the material is incorporated into a filter, and then the air is drawn into the collector to be captured by the filter. So basically, carbon dioxide binds to the material inside the filter. And once the filter is saturated with carbon dioxide, the collector is then heated in order for the carbon dioxide that was captured to be released. which we call regeneration, so that the filter will be regenerated to be used for subsequent carbon capture events. So my research work here at Argonne focuses on, number one, understanding how these materials can capture carbon dioxide directly from the atmosphere on the molecular level. And number two, and more importantly, is to work to enhance this capturing efficiency. And to do so, we use a very advanced laser technology called some frequency generation spectroscopy. So to do this, so this tool or this technique, it tells us or gives information or like signatures on chemical species or chemical materials on surfaces and hidden interfaces. So the way it works, we overlap two laser beams, one in the infrared region and another one in the visible region. And upon overlapping them, some frequency generation light will be generated. And by analyzing this some frequency generation light, we can extract information on the chemistry at the surface we are studying or the hidden interface. So this tool works the same way as an infrared laser barcode scanner that we use in a grocery store. So how do we use or make use of this technology in our project? So simply, if we want to test whether a chemical can capture carbon dioxide from the atmosphere or not, we expose the surface of the chemical to air that's rich in carbon dioxide while shining it with the laser beam. And if carbon dioxide is captured by the chemical and enhanced onto the surface, we see signatures or like a fingerprint of carbon dioxide, which tells us that carbon dioxide is enhanced on the surface. And on top of that, if carbon dioxide is transformed or converted to other chemical species like carbonate or bicarbonate or whatever, we still see signatures of these new chemical species. So yeah, here are like some data that from our research. So for example, as we see on the left figure or the left panel, so the red spectrum with the red rays shows that when carbon dioxide is absorbed or captured at the surface, so we see a signal. So this signal is very specific to carbon dioxide. And the black spectrum, like this, was in the absence of carbon dioxide. And the right panel showed that when we increase the exposure time of our chemical to carbon dioxide, we start to see the conversion of carbon dioxide to new species. So specifically, this feature is due to the new carbon capture product, which is carbonate or like bicarbonate species on the surface. So this is a very advanced technology, and it's helping us to understand how certain materials can capture carbon dioxide, also the chemical reactivity of carbon dioxide on the surface, and also the products that are coming from the capture process. So with this technology in hand, we were able to do real-time analysis of the capturing carbon dioxide over time, as well as the in situ testing. And also, we can monitor or have real-time monitoring of the behavior of these chemicals over time, like the lifetime of the chemical sorbents. And so far, we are excited that we have discovered new materials in our research that can work for capturing carbon dioxide from the atmosphere. And inspired by that, the next step can be to try to, upscaling or trying to incorporate these materials into the direct air capture plant so that they can be like new candidates added to the toolbox of the chemical sorbents that are already used as benchmark sorbents for carbon dioxide in the direct air capture plants. So I think this kind of research is promising in our fight against the global warming and the crazy climate changes we have been suffering from. Yeah, thank you.
Yeah. Thank you, Mokhtar. I will now ask for our last speaker of the evening to join me on stage, and Bethany Dean-Kersten will give her talk titled Recycling Nuclear Fuel Unlocks the Potential to Recover 100 Times More Energy. Bethany, the floor is yours.
Awesome. Thank you, Sean. Well, we just heard some phenomenal talks about humanity's exciting future with supercomputing and artificial intelligence, and also the balance that we must strike in depending on these energy-intensive technologies, since our energy grid still mostly depends on fossil fuels. And so with that, depending on these energy-intensive technologies results in more greenhouse gases being emitted. Well, today I'm excited to share with you an energy solution that does not emit greenhouse gases, and that is nuclear power. Nuclear power already generates a fifth of the energy that goes into our electric grid, and nuclear power outshines power generated by fossil fuels. Not only does nuclear energy not emit greenhouse gases, but the amount of fuel that is needed to produce the same amount of electricity as coal or natural gas is minuscule. Nuclear power is just as dependable and online as fossil fuel generation, and we can imagine a future energy economy where nuclear energy works hand in hand with wind and solar power, as it can provide electricity when the wind isn't blowing or the sun isn't shining. I could go on and on about the obviously positive aspects of nuclear power, but today I want to focus on one of its last really remaining challenges, which is in dealing with the used nuclear fuel. And surprisingly, I'm going to convince you all today that it's actually a not so obvious positive aspect as well. Argonne has been working on really exciting research and improving ways we can provide Americans with clean energy by recycling used nuclear fuel. So used nuclear fuel is what the nuclear industry refers to nuclear waste. And when I say nuclear waste, you may have a certain image pop into your head. In reality, nuclear waste looks like these long stainless steel tubes that have small pellets of uranium and some byproducts. Now, these byproducts are very radioactive and radioactive for thousands of years, which is why it's so hard to deal with these elements. But we can actually recycle over 95% of used nuclear fuel to recycle back into a reactor. Since the 1950s, the US has been generating used nuclear fuel. Although that's a long time, that amount of waste would actually fit comfortably inside one football stadium. With recycling, we could further decrease that footprint down to the size of one Olympic-sized swimming pool. And although it may sound like a buzzword, radioactivity is something that is widely understood and can be handled safely. With recycling and pulling out that 95% of the waste, the amount of the waste that's left, that 5%, is much less radioactive. And so when we go to manage a facility and storing that waste, we only have to take care of that for a few hundreds of years, compared to we would need to take care of it for eras, hundreds of thousands of years, if we did not recycle. Recycling used nuclear fuel is not a new concept, and Argonne has been doing this since the 1980s in research with molten salt electrochemical separations. Molten salts are literally like the table salt you have at home that are melted at very high temperatures where they behave as a liquid, and they're super conductive, and that's super helpful for the electrochemical separations. And electrochemical separations use the same reactions and concepts that we use to charge a battery, like the one in your cell phone or in your car. So to charge a battery, ions are dissolved into a liquid media, one that's water-based or like an acid, and these ions are moved from an anode to a cathode by the movement of electrons or current. And so to recycle used nuclear fuel, we dissolve the used nuclear fuel in molten salt, where current pushes the recyclable elements from an anode to a cathode, where it's collected as a metal and can then be made into new fuel again. My research is in implementing sensor technologies. These sensors can be placed at almost any point in the recycling facility and can withstand high temperatures and radiation. These sensors tell us very important information about the state of the reactions that are happening in real time, and also the concentrations of important elements like uranium and plutonium at all times. These pieces of information allow us to increase process efficiency, decrease operational costs as we can tune the knobs on this process in real time as a result of gaining that feedback, and then we are enhancing our security by being able to pinpoint these elements in real time. Recycling used nuclear fuel allows for 100 times more energy to be harnessed from the fuel that we are mining from the ground. It reduces the physical footprint as well as the radioactivity drastically and allows nuclear power to become even more sustainable. So to keep powering that important AI to benefit human health and our well-being, and also decrease the contribution that we have on the environment with greenhouse gases, recycling used nuclear fuel unlocks the potential for nuclear power to provide millions of people electricity for generations to come. Thank you.
Thank you, Bethany. We are now at the point of the program where we'd love to hear from you, our audience members. Now, before we get to your questions, Shilpika and Mokhtar, please join us up on stage. For the in-person audience, we have one mic stand, and if you have a question, please come to the microphone so that we and our online audience can actually hear you. If you're online, we ask that you type your question into the chat, and we will pose it on your behalf to our panelists. So we'll get to as many questions as we can for the evening. All right, so we do have one question. Please.
Sure. My question's for Mokhtar. Given the presentation we just heard about the radioactivity, it's been about 80 years since we can recycle. For the carbon capture, I've read they've already been talking about large transit tubes for the captured carbon in some plants. Are they looking at how to recycle the CO2? I mean, it's carbon chemistry. It's like potentially highly usable, one would think. Are they looking at anything to process the carbon that they capture?
Yeah, so you mean like after capturing carbon dioxide, what do they do with it? Yes. Yeah, so basically, so for the direct air capture plant that I talked about, so each plant has its own like objective. For example, there is the Climwork company in Europe, so that's the main direct air capture company. So what they do is they do like mineralization of carbon dioxide. So basically they react it like with rocks to convert it to carbonates, for example, like calcium carbonate, magnesium carbonate, or so. Some other direct air capture plants, they store it to use it for like oil drilling. So like, I'm not familiar with that, but there are for sure after capturing it are already like some processes that carbon dioxide can be like transformed to minerals or used for like oil exploration. So it's not just about like capturing. Thank you.
I'd like to take a question from online.
Sure. We have a question from John West. Will you also be able to process our low-level stuff like AM-241 from smoke detectors?
Yeah, that's a great question. Yes. I actually did, this is a fun fact, I did some graduate research using americium-243, which is not the one found in your smoke detector, but yeah, you can definitely recycle those and could be put into an advanced reactor.
We've got one in the room.
So all of you are just this little tiny piece of this giant network. And I would imagine that your little piece has to network somehow with other organizations and companies. And so as the sensor person, who is the conductor of the bigger picture? Is there a conductor? You know, is there somebody who says, oh, Bethany, we need this sensor? Or, oh, please work on the lasers. Who is doing it? Who is the person directing?
That's a very interesting question. Thank you for that. I think we'll let our early career researchers take a stab, then I might come behind them. Does anybody want to take a stab at that? Okay, great.
Yeah. Well, working for a Department of Energy national laboratory, we get a lot of our encouragement and funding for research from them. But we also work a lot with, like me personally in my research, with private industries. So working with, for example, nuclear power companies that want to incorporate recycling in their future designs. And so they're interested in these sensors and these technologies. And it's really the key of getting both government support as well as that private industry to get everyone to work together. And I think, yeah, Argonne is situated very nicely where we get to do that every day.
That's an excellent answer. Would anyone else like to add?
I will speak about my project. So, my project is, as you saw on direct air capture of carbon dioxide. So, this project was coming from like a research call, from the Department of Energy. So it's actually in a collaboration with the Professor May Nyman from Oregon State University. So I think every, I would say like 3 years, there is a call for the big or the big challenges or big problems, like carbon dioxide is one of the, or like the global warming is one of the big problems these days. So here in the United States, for example, there are always research calls for this kind of problems. So it's funded by the DOE, and like for our project, for example, it's collaboration between Argonne, like some other universities. So that's how it worked for my project.
So in my case, we have these supercomputers, and when I first started working, it was a big computer, a supercomputer at the time, but then it keeps growing and growing and growing. And some of the methods that I worked on a previous supercomputer, Theta, doesn't really, it works, but the scale of the data that we work with and we have to deal with right now is different. And we have users with applications running on these machines. We've moved on from traditional AI models, neural networks, to all of these large language foundation models, which can take months or even years in some cases to train and to run. And we cannot have users experiencing problems, and even the facility, we cannot have a part of the machine not working or giving us wrong results. So it's important from all sides. They're like, get us the information we need. This is helpful. So it's always on the priority list. Keep these machines working.
Yep. Phenomenal answers, and really appreciate your thoughtful approach to that. I'll just add, one of the beauties of working in science is that it's a full ecosystem. And our communities meet regularly to discuss these grand challenges, and then to say, here are the most important questions to answer to solve these grand challenges. And being at a place like Argonne, you're equipped to really answer those kinds of questions. So it's a community-driven approach, and we actually are part of a smaller ecosystem within the larger ecosystem, and that's the Department of Energy National Laboratory ecosystem of 17 national labs. So as you heard from the answers here, we're connected to other labs who are also equipped to answer really grand challenge, really large questions. And we sort of divvy up, with your expertise, you should answer these questions. And for these questions, maybe you're better to answer those. And so through a community approach, working with our partners who are also equipped to solve these grand challenges, we can move these things forward. So it's not one person per se, but it's a community agreeing over and over and over again about grand challenges and the solutions to them. That's a very fascinating question. Thank you.
Hi, thank you. This is for Bethany. So is it paraprocessing that you're talking about?
Yes.
Okay, so when we deal with the nuclear waste that way, what are the waste products that come out of that process, and what do we do with them?
Yeah, so really, that 5% of the nuclear fuel that isn't helpful to put back into a reactor, that does go into what's known as a metal waste form or a ceramic waste form. And those can be placed into containers that are then stored depending on where the US government decides to do that, whether that's underground, whether that's on site at a facility. But that's what it could look like. And the products that those include would be products like some gases that could be captured, or also just some metals that, again, act more as a poison inside the reactor. It doesn't help contribute to the reaction. And so, yeah, those are just taken out, and they decay. Again, the radioactivity of it decays much faster than the radioactivity of the elements that can be recycled.
So just a quick follow-up. So what I'm really interested in is not the things that come from the original waste, but things that are part of the process, the molten salt, other things that might need to be disposed of. What do we do with that?
Yeah, definitely. The molten salt actually is recycled in loop in the process. And so really, most of it is kept within the process and it doesn't really degrade over time. But it can also be used to stabilize the waste that does have to be packaged out. So talking about those elements that can't go back into a reactor, the molten salt can be used to help stabilize it as it goes into that container to then be stored.
Let's take a question from online.
Right, John asked, will Aurora's power be used to design your next quantum computer?
Shilpika, that one's for you.
Could you repeat that? I'm sorry.
Yeah, sorry, Shilpika. Will Aurora's power be used to design Argonne's next quantum computer?
I'm not really sure, but if it's possible, why not?
Okay.
We are not holding ourselves back here at Argonne.
All right, we have a question on this side of the room. Son, you done?
This may be a stretch for Bethany, the process you described, but is there any applicability to cleaning up a disaster site like Chernobyl or a 3 Mile Island?
Yeah, pyroprocessing is mostly, it's designed to process waste that comes directly out of a nuclear reactor. So really its applicability for being able, you first need to collect all of the waste that could be scattered from a disaster. But really it's not really designed for that type of application.
All right, we'll take one question online.
Lots of questions for Bethany. Does recycling of fuel rods project cost savings for unit kilowatt hours?
It can. I think also what is out there on the internet, if you look that up, is that recycling in general is not always the most cost-saving thing if you're only talking about dollars. But I think the cost in terms of environmental cost is huge if we don't recycle. And so I think that's also really important to think about.
All right, we've got one question in the room here.
Yes.
Hello. This is kind of a non-technical question, but I'm a local engineering computer science high school teacher. And so I come to these things and curious about what's going on in the neighborhood here. And my question to you guys, and anybody can answer this, when I send students to universities to study A, B, and C, and you guys are coming up with all these really cool applications of what you studied, I assume you're on a team full of a variety of backgrounds and intellectual pursuits and things like that. Can you give me a flavor for maybe a small team that you're part of that kind of coalesced to make these studies happen? And I know computer science is a part of probably all of it, and I'm curious how much that's growing, I assume exponentially. That's my question.
So in my team, we have mathematicians, we have people who are very focused on running their applications and parallelizing them and running them on the supercomputer. And we have even statisticians who help us. We have AI experts. So it's really people from various fields that are helping us because we have these packages that run on the machine, and we want to make sure that the results they give us are correct and they are reliable. So we have to make sure we have these teams, these experts, not just not just people who are doing the math, but also people who can code and then understand the hardware of the machines. So it's really everyone from all fields that you can think of.
Yeah, in my case, yeah, for my project, it requires like multidisciplines. So, for example, starting from designing and doing the synthesis of the materials that we're gonna test for capturing carbon dioxide. So, for example, our collaborators in Oregon State University, they work on the synthesis of these compounds, and from their side, so they do the synthesis. They also they have the experts in the characterization and the analysis, using like some analytical tools. And from our side, because I'm mainly interested on studying the interaction of carbon dioxide with the surfaces and the interface of the material that is synthesized, so that requires expertise in spectroscopy. So me and my supervisor, we have expertise in laser spectroscopy, specifically in that technique, some frequency generation spectroscopy. And yeah, so it's not just this. We are so the project, it's my PI project in our group, but at the same time we have a diverse group. So the group has, like, even if they are not involved in the project, so in our weekly meetings and the group meetings, so they are insightful discussions because they are also experts in like research areas related to that can be relevant to what we are doing, like extraction, gas separation, like heavy elements and so on. So it's not, it cannot be, this kind of research cannot be done by just one person, one or two persons. So it has to be a kind of a wide spectrum of experts. So like I said, like inorganic chemists, spectroscopists, and also something that I haven't talked about in my talk, there is also computational calculations that we run to kind of complement or support our findings. So yeah, it's a multi-discipline process. Yeah.
Yeah, similarly, in teams that I've been working with, you definitely have computer scientists and working in the nuclear field, nuclear engineers and nuclear chemists. But something really exciting in the nuclear field is you don't actually have to have a nuclear educational background. So I'm a chemical engineer, and I work with many chemical engineers and physicists. And also people have studied also writing, because that's a key important part of being a scientist, being able to write your reports and your findings. And also people have had communication backgrounds. That's extremely important. And also digital art has been huge too, being able to paint a picture really clearly of what's going on. So being able to do the science and also portray it to be easily understood, that makes the best team.
All right, let's take an online question.
All right, we have one for Mokhtar from Nancy. For carbon capture, how many materials are good candidates and how soon might they scale up?
Okay, that's a good question. So far, speaking about my project, we we have explored a number of materials, and we have already some of our work has been published. So far, we tested, I would say, 3 to 4 different systems. And yeah, we have in our bucket list, we have like many more to test. So we have the knowledge, and so it's easy to, if we build we have our system and we know what we are doing, so we can explore as many as we can. So that's for the first part. For the second part, for the upscaling, so yeah, this is the most challenging part. It's not easy to go from the bench scale to the pilot or the industrial scale. So I have no clear answer for that for now, but we are hoping to and soon to upscale or incorporate the successfully explored materials into large scale operations soon. Yeah.
Okay, our last question of the evening will be here in the room.
Yes, hi, this is for Bethany. It sounds like your nuclear waste process is a vitrification process, correct? Where you're mixing it or turning it into a glass?
the very end, that is one way. Yes, you can take that 5% of the waste, and yeah, you can mix it with glass. That's one waste product.
Okay. What kind of power is used to take the nuclear waste? I guess you're going to liquefy it and then separate it, correct?
Yeah. So when you take the fuel out from the reactor itself, it's metal pellets. Those are basically, they can go right into a molten salt. And the electrons that move through this system actually dissolves the metal into the liquid. And so, yes, you are pushing current through, but it's very low voltage. And so the power actually isn't that high needed for that.
Would this be something that could be used like at all the nuclear generating stations? Because that's where they actually store their waste, correct?
I think that would be ideal, yes.
Great. Well, thank you so much for your great questions. They really added to our robust discussion and to these fabulous presentations. We apologize we're unable to get to all of the questions. I know there were a few additional ones in the room. I actually had a few myself. But you can actually email your questions and any feedback to outloud@anl.gov. And again, any additional questions or feedback, and we will get back to you with some answers. I'd like to close by thanking each of our speakers for their contributions tonight. It was an outstanding discussion. And finally, we thank you again for joining us tonight. And we hope that you enjoyed the discussion, and we hope that you'll enjoy and join us again at our next event. Please have a safe trip home. Thank you.